Good day everyone, my name is Graphics. Today we'll be looking at the air refrigeration system working on Coleman cycle, or you can call it the Joule cycle, or you can call it the reverse Brighton cycle. Now we'll be looking at the processes involved in this cycle termed Coleman. So let's start. Process involved. Now there are four processes that is involved in refrigeration system working under Coleman cycle. But first of all, what do you understand by the word process? A process is when a system changes from one state to another, series of states. And we know in a Coleman cycle we have four states, which are four states, like I said earlier, four states, four process, and what? One cycle. When we move from state 1 to state 2, we have 1, 2, 3, 4. That is 4 states. When you move from state 1 to state 2, it is called a process. When you move from state 2 to state 3, is another process. When you move from state 3 to state 4, is another process. When you move from state 4 to state 1, is another process. But when you move from 1 back to what? To 1, you have undergone a cycle. So we have four processes in this Coleman cycle. The first process that we have is called the Isentropic process. We have what is called what? The Isentropic process. The Isentropic process, the isentropic compression process is also called the reversed adiabatic compression process. Now, at this process 1, the process 1 occurs between state 1 and state 2. So it occurs between what? State 1 to what? To 2. That is when the isentropic compression process. Now, the refrigerant, which is the air, is moving into the compressor. In the compressor here, the entry of the compressor, which is state 1, this is when the refrigerant is moving, the cooled air is moving into the compressor. When the cooled air gets into the compressor compresses the air in an isentropic process, or compress the air isentropically, right? Whereby increasing the temperature and also increasing what? The pressure of the air without the help of heat input or heat output. Is that taken? Now this is what they mean here. Let's show this in our PV and TS diagram. So this is state 1 here, right? Now what happened? When the refrigerant enters the compressor, it increases the pressure. It does what? It increases the pressure from state 1 to state 2, and it does that isentropically. So as it does that, at state 1 in the TS diagram, what happened? The temperature at state 1 is increased also to what? To state 2. How good? So we use a straight line to represent it. Now, as it enters into compressor and comes out at state 2 here, which is the exit of the compressor, what happened is already having a high pressure and what? And high temperature. Start taking, and the volume is what? Is reduced. This is V1, right? And this is what? The volume is reduced to what? V2. Is that taken? Now, at state 2, which is the entry of the cooler, what does the cooler does? It decreases the what? The temperature of what? Of the refrigerant, which is the air to be cooled. So at the cooler, there is what? There is heat rejection by the system. The system is the what? Is the air, which is the refrigerant. There is heat rejection at what? at the cooler. But this is at that state 2. We have done from state 1 to state 2 now. At state 2 and 3, we are going into what? A constant pressure cooling process. A constant pressure cooling process. And that occurs between 2 and 3. Between 2 to 3. There's a constant pressure what? Cooling process. Now, you see when this refrigerant has entered the compressor, when it comes out at state 2, the temperature of the refrigerant is high, the pressure is high, and the volume has been reduced to what? To V2. Right? This is the temperature here. This is T1. This is the pressure here, which is what? P1, right? And the temperature here, which is what? T1. We are doing them simultaneously. So the temperature is what? Is increased here at state 2, and the pressure is also increased. So as it enters into the cooler, what happens? There is an heat rejection. The refrigerant here is cooled. As it's cooled down, it means that what? The temperature of what? Will reduce. Temperature has reduced to what? From state 2 to state 3, the temperature reduced. So from this state here to this state here, at this state 3, the temperature has already reduced. But what? The pressure also remains constant. So from 2 to 3, the pressure remains what? Constant. That's why we call it constant pressure cooling process. During the cooling process, there is no change in pressure. Is that taken? So we say our P3 is equal to what? P2. Only temperature what? We reduced. But what happened? The volume has furtherly reduced to what? To V3. At state 2, at process 2, which is constant pressure cooling process, we say there's an heat rejection there. So we say our heat rejection, that is QHR, occurs between state 2, Q23, right, which is at constant pressure, because between 2 and 3 there is a constant pressure there, right? So CP. Then what happened to the temperature? The temperature is what? Is reduced. So T2 is higher than T3. So we're having T2 minus what? T3. So we should know this. At constant pressure, we're having this. Right? Now we'll move forward. The next thing we're talking about will be isentropic expansion process. At the isentropic expansion process, which is also called reversible adiabatic expansion process, right? What happened? It occurs between state 3 to state 4. The liquid at state 3 enters the expander, where it is expanded isentropically. So at the expander, the temperature of the refrigerant furtherly reduced to state 4, right? And what happened to the pressure? At state 3 to state 4, the pressure is what? Is reduced from 3. Look at the pressure here, is coming down to state 4, while the volume is furtherly reduced to what? To what? V4 is increased to what? At state 3 to state 4, the pressure is what? Is reduced, while the specific volume is what? Is increased. And between state 3 and state 4, the temperature is also what? Reduced. So at the expander, both pressure and temperature is reduced isentropically, right? Is reduced without the addition of heat without the addition of heat or the reduction of heat, So the air from the cooler is now drawn into the expander here at state 3. So the next process that we'll be looking at will be the constant pressure expansion process. So we're talking about the constant pressure expansion process. The constant pressure expansion process, it occurs between states what? 4 and what? 1. It occurs between state 4 and 1. Constant pressure expansion process occurs between state 4 and 1. What happened between state 4 and 1? State 4 and 1 is the refrigerator. In between the state 4 and 1 is what? Refrigerator. At the refrigerator, what happened? When the refrigerant enters the refrigerator, we expect there should be cooling in the refrigerator because that is our desired effect. So what happened here? There is a heat gained here. The refrigerator here absorbs heat, so there's heat absorbed here. Heat absorbed at the refrigerator. So in between state 4 and 1, there's heat absorbed there, right? So as the heat is being absorbed in the refrigerator, what happened? The refrigerant increases in what? In temperature. So if you watch it very well here, there's an increase in temperature here, right? From state 4 to state 1, while at the refrigerator, nothing happens to the pressure. The pressure remains constant. So that's why we call it constant pressure expansion process. So now in the refrigerator, like I was saying, in between state 4 and 1, we have our QHA, heat absorbed, is what? In between state 4 to 1, right? And that will give us, it happens at what? Constant pressure, to give us T1 minus T4, because the temperature of T1 is greater than that of what? T4, right? So this is what we are going to be having here. To know how to draw our TS diagram, this is the TS diagram here, and don't forget to always put your arrows to show the direction of movement of the refrigerant. So this is our TS diagram, right? This is, now we'll move forward. So the next thing we're talking about now will be COP in an isentropic process. So we want to look for the coefficient of performance in an isentropic process. So we know that COP, coefficient of performance, is equals to what? The desired effect. The desired effect all over what? The work input, right? Now, or the work done. In a refrigerator, we need a work input. Now, if you have a refrigerator at home, what you really want from your refrigerator is what? Cooling, right? And the cooling happens in a what? In a low temperature. Is that taken? So in this case here now, where does the cooling happen? The cooling happens at the refrigerator, and the refrigerator is in between what? State 4 and state 1. So we'll come here, our desired effect at the refrigerator is equal to what? QHA. And in the refrigerator, why I put QHA means there's heat absorbed in the refrigerator all over. The work in is always what? The heat rejected, QHR, minus what? The heat absorbed, QHA. Is that again? So from this aspect here, we'll move further by saying that my QHA is given as what? It's given as Q4 to 1 all over QHR is given as what? Q23 minus Q4 to 1. So we are going to input our value here now. So inputting the value here, we'll be having Q4 to 1 is what? CP into bracket T1 minus T4 all over Q23 is what? Cp into bracket T2 minus T3, close the bracket, minus Cp into bracket T1 minus T4. So this is what we're having here. So from here, since Cp is common, I'm going to bring Cp out of the equation. So we're having Cp into bracket T1 minus T4 all over Cp into bracket T2 minus T3 minus T1 minus T4. So we close the brackets all. Now Cp will equal Cp, and we'll all be left with T1 minus T4 all over T2 minus T3 minus T1 minus T4. So this is what we're having. We are going to bring my T4 out of the equation. So bringing T4 out means we are going to divide both sides by T4. This is what I mean. If I bring T1 minus what? T4 into brackets. Once I bring out my T4, I am going to divide by T4, and I'll divide by T4. Is that again? I'm going to divide by T4. So all over, if I bring T3 from my equal sign, I'm going to bring out what? I'm going to divide both sides by what? T3. So if I bring this T3 out here, I'll be having T2 over T3 minus T3 over T3. I'll close it up. Minus the same thing. I'll do the same thing for the other aspect too. So I'll be having T1 over T4 minus T4 over T4. Now in doing that, T4 over T4 is 1. So I'll be left with T4 into bracket T1 over T4 minus 1 all over T3 into bracket T2 over T3 minus 1 minus T4 into bracket T1 over T4 minus 1, because these two will equate each other. This one too equate each other. This equate each other. We are left with what? With 1, right? Now we need to understand something. In our compression process, either compression and expansion process, we know that if you look at this, it's always the high side minus the low side. So we know that P2 is a compression happening here between state 2 and 1. So P2 over P1 is equals to what? T3 over T4, right? So I'm going to write that recall in expansion and compression process, P2 over P1, since it's adiabatic, reversible adiabatic, I will have my gamma minus 1 all over gamma, right, is equals to what? T2 over T1. This is what I mean here. If you look here, P2 over P1 is equals to what? T2 over T1. Also, this is P2 over P1 is the compression process, but and P3 over P4 into bracket gamma minus 1 over gamma is equals to what? T3 over T4. So you should always remember that it is the higher minus the lower, T2 over T1 because at this point here we say this is the what? The high pressure side, right? So the high pressure side divided by the low pressure side. Always remember that. So we move further. Now in this case now we know that P2 is equal to, but P2 is equal to what? P3, and P1 is equal to what? P4. Because of what? It is constant process, right? So we say P2 is equal to P3 and P1 is equal to what? Is equal to what? P4, right? So it means that this is equal to this. It means this is equal to what? This. So we'll now say P2 over P1, P2 over P1, gamma minus 1 over gamma is equals to what? P3 over P4. We have this minus 1 over this. Then T2 all over T1 is equals to what? T3 all over what? T4. So this is how it is. So in this case, if I cross multiply, I'll get to understand that if I take this T3 down here, then my T2 over T3 will be equals to what? T1 over what? T4. So I take this up and I brought this down, and I take how I just did. So in this aspect, we see that T2 over T3 and T1 over T4 is the same. So it means that what? From this equation 1 here, this will equate this, at the same time equate this, because they are all equal. So I'll now say therefore T4 all over what? T3 minus T4. So our COP, I will now divide both the numerator by the denominator by what? T4. So dividing up and down by T4, I'll be having T4, let me put it here. So now give me T4 over T4, because I need to make this man here equals to 1, all over T3 over T4 minus T4 over T4. So at this case, this one will become 1. So I'm going to be having 1 all over T3 over T4 minus what? Minus 1, right? But T3 over T4 is equals to what? So I'll put it, but T3 all over T4 is equals to what? P3 all over what? P4 raised to the power of what? This minus what? Minus 1 all over this, right? So if I move forward, and this is our expansion process, right? So from here I will now have my COP is equals to 1 all over P3 all over what? P4 raised to the power of what? Gamma minus 1 over gamma minus everything minus 1, and this over this is called our what? So the COP will now be P3 over P4 is our compression ratio. So I write my ROP raised to the power of what? Gamma minus 1 over gamma minus 1. So whenever we are told to look for our COP, we can use this formula, or we can use this formula here, or we can use this formula here, COP, right? Or we can use this. So don't forget that. So This is when we are dealing with isentropic compression, right? So let's take an example and see how we are going to solve question using this particular formula here. So example 1. Here it says an air refrigeration system operating on a Coleman cycle draws air from a cold chamber at a pressure of 1 bar and the temperature of 10 degrees centigrade. It's then compressed in the compressor up to a pressure of 5 bar and after being cooled at constant pressure up to a temperature of 40 degrees centigrade. It enters the expander. It enters the expander, assuming both expansion process and adiabatic process to be what? Isentropic. Calculate the COP of the system and take constant pressure of air to be equal to 1.005 kJ per kilogram Kelvin and our gamma to be equal to what? 1.1. Now one thing you need to understand is this. The key word here is that it's telling us that what? It says both expansion process and adiabatic process is what? Isentropic. So what we have to do is that what? We are going to use our COP, right, to be equals to what? 1 all over RP 1 over 1 all over P3 over P4, everything raised to the power of what? Gamma minus 1 over what? Gamma, everything minus 1, right? So that is what we use for our what? Our COP, and we just proved it. So what you do is this. Now let's write out our parameters. It says an air refrigeration system operating in a Coleman cycle draws an air from a cold chamber at a pressure of 1 bar. So when it draws air at a pressure of what? 1 bar. So where is the air drawn from? The air is drawn from the refrigerator into the compressor. So you said the pressure at this state here between state 1 and state 2 is what? 1 bar. The pressure at state 1 here is 1 bar. So my P1 is 1 bar. P1 is equals to what? 1 bar. Right? And we know P1 is equals to what? P4. Look at it very well. P1 is equals to what? P4. P1 is equals to P4 from that graph. We need the graph to work. So P1 is equals to what? P4. And also and temperature of 10 degrees centigrade. So our T1 is equals to what? 10 degrees centigrade, which is equals to what? 10 plus 273, which will give us what? 283 Kelvin. That is one stage. Now the next thing is it then compressed in the compressor. Now it has entered the compressor up to a pressure of 5 bar. So it enters the compressor up to a pressure of what? It's compressed in the compressor up to a pressure of 5 bar, and after being cooled at constant pressure up to a temperature of what? 40 degrees. So our P2, because after being compressed in the compressor to be at what? State 2. So P2 is equals to 5 bar. And we know P2 is equals to what? P3 is equals to what? 5 bar, because the pressure is what? Is constant, right? Now that is at this state here now. Between state 2 and 3, the pressure is equal. Are we good? The pressure is equal. Now, if you look at this, and after being cooled, when it's after being cooled, look at what does the compressor does? What does the cooler does is to cool the air coming in. So when you have enter, it said after being cooled. After being cooled is at state 3, right? So it said after being cooled at constant pressure up to a temperature of 40 degrees. That means our T3 our T3 is equals to 40 degrees. So don't forget that after being cooled, T3 is equals to what? 40 degrees centigrade. So we say 40 plus 273, and that will give us 313 Kelvin. So don't forget that. So we know about T3, we know T1, but we don't know T2, and we don't know T4. So T2 is unknown, and also T4 is unknown, and because it says it enters the expander assuming both expansion and compression process is adiabatic to be isentropic. Calculate the COP of the system and take CP, constant pressure of air, to be 1.005 kilojoule per kilogram Kelvin, and you take your gamma to be equals to what? That is 1.4. So what you just have to do, you put your value here. Since I already proved, if you have to prove, just use this formation and you'll be having this from here. See what I want to do. So it will be 1 all over P3 is 5, that will be 5 all over P4 is 1, so we'll be having the gamma here is giving us 1.4 minus 1 all over 1.4, everything subtracted by 1. So this will be giving us 1 all over 5 raised to the power of 0.4 over 1.4, everything minus 1. So if you do that, 0.4 over 1.4, 0.4 divided by 1.4, that will give us 0.285. So we'll be having this to be equals to 1 all over 5 raised to power 0.2857 minus what? Minus 1. So 5 raised to the power of answer, we're having this to be equals to 1 all over 1.5838 minus 1, because 5 raised to power this will give us that. 5 raised to power this will give us that. So that will give me 1 all over 0.5838. So from here, if you divide minus 1 divided by answer, so if you divide this in your calculator, you are going to be having 1.713. So that is our COP to be our answer of that system. So this is when you are giving, you've proved. So our COP is 1.713. Now the alternative method here is this. You are going to calculate these things individually if you are not told to prove. Now because we proved our formula, that is why we're able to get this. So alternatively we'll be having we know very well that our P2 all over P3 raised to the power of gamma minus 1 all over gamma is equals to T2 over T1, equals to T2 over T1. Now what will happen here is I am looking for what? I'm looking for T2, right? So I'm going to make T2 the subject of the formula. So in doing that, my T2 will be here and my T1 will go and multiply this. So P2 over P3 all over, raised power gamma minus 1 over gamma. So I've taken this to this side, multiplied by what? T2. T1, sorry. So the question is, what is my T1? My T1 here is what? 283 Kelvin. So my T1 is equals to what? 283 Kelvin multiplied by my P2 here is given as 5 bar. So my P2 is given as 5 bar, and my P3 and my P2 is given as what? 5 bar, and my P3, careful, P2 is given as what? 5 bar, and P1 is given as what? What is the P1 here? That's given as 1 bar, right? So we have 1 here. Everything is the power of what? Gamma is 1.4 minus 1 all over 1.4. So equals to what? T2. Therefore my T2 will give me 5 raised to the power of, no one calculated this now, we say everything here, everything up here is giving us 0.2857. So I will just put it here, 0.2857. So my T2 will now give me 5 raised to the power 0.2857, and that will give me 1.5838 degree multiplied by 283. So multiplied by 283. So 1.5838 multiplied by 283, 448. So T2 is equals to 448.21 Kelvin. That is T2. Then for the other aspect, we need to get what is because we're looking for T2 and T4. Gotten T2, so we'll try for T4. So for T4, we will say it is P3 over P4. We'll be having P3 over P4 raised to the power of gamma minus 1 over gamma is equals to what? T3 all over T2. So from here I'm looking for what? I'm looking for T3 over T4, sorry. T3 over T4. So from here I'm looking for for what am I calculating for now? I've gotten my T2 here, right? So the next thing is I'm calculating for what? For T4. So I can help myself here. Now initially I said P3 over P4 is equal to T3 over T4, but I can interchange it. If I write P4 up here all over P3, right, I can also do the same for here. I write T4 over what? T3. So I've not done anything, because what I did it for both sides. So what will I do? I'll see my T4 is equals to I'll be having P4 over P3 raised to power gamma minus 1 over gamma times T3. I cross multiply this to this side, right? So I rewrite it out. So from here I can say that my T4 is equals to, what is P4? P4 is 1 all over P3 is 5 raised to the power of 1.4 minus 1 all over 1.4 times T3. So what is T3? T3 is 313, because I'm giving it the parameter here. And T3 is equals to 313 here. So what I will do here is this. I will say the T4 will now be equals to 1 divided by 5. 1 divided by 5 is 0.2. 0.2 raised to the power of 0.2857. When you do this, multiply everything by 313. So if I do that, 0.2 raised to the power of 0.2851. That will give me 0. Let me do it here. So my T4 will be giving me 0.632 multiplied by this guy here. Multiplied by this guy here. 313. So I have my 313 here. So times 313. So I'll be having 197. So my T4 is equal to 197.81. That's my T4 here. So now if you remember this formula I told you, COP also can be calculated with this, right? So this is what I wrote here. So we know what T1 is. Our T1 is given as T1 is giving us 283. Can you see that? So 283 minus T4. So what is T4? T4 is giving us what? 197.81. So it's giving us 197.81. So we have 197.81 all over T2. T2 here is giving us this. T2 is giving us 448.21. So we have here 448.21 minus T3. So T3 is giving us 313. So we have 313 minus 313 minus 283 minus 197.81. That's what we're having here. So from here we can do our work here. So if you subtract this two, you'll be having 85.19 all over 135.21 minus 85.19 equals to 85.19 all over. Now if you subtract these two, you'll be having 50.02. Now if you divide 85.19 divided by answer, you'll be having 1.703, right? Approximately 1.7. So that's what we're having. So that is the COP. So either you follow this process or you follow the other process. You see here we have 1.7 approximately, and also here we have 1.73 approximately. So any one of your choice. Thank you very much for watching.